In this graph, going from A to B, our x changed by this much and correspondingly our y changed by this much. Then our average rate of change of delta y by delta x is slope of line AB. You can write it here. Delta y by delta x and slope of AB. To identify delta y and delta x, you can see here, this is our delta x and correspondingly y changed by this much amount going from A to B. Our delta x here is this quantity and delta y is really this quantity. And you can see slope of the line AB is tan theta, which is delta y by delta x. That's why we are calling it delta y by delta x is equal to slope of line AB. The average rate of change of y with respect to x tells you on an average how y is changing with x, which is simply whatever is the change in y divided by whatever the change in x is. Let's move to a very crucial question, that how to find the rate of change of y with respect to x at any point on the curve. Can we find the rate of change of y with respect to x at point A or at point B or some other point on the curve? So let's say we want to find the rate of change of y with respect to x at point A. Keeping that question in mind, let's try to understand how this average rate of change can be manipulated to get the instantaneous rate of change of y with respect to x at A. So in order to get the instantaneous rate of change of y with respect to x at A, or the instantaneous rate of change, we have to make our reading close to point A by moving point B close to point A. The more closer we can get, the more accurate will be the reading. Now let's see what it means if we move point B on the curve. Let's try to understand what happens to delta x. We have first point to remember is the average value delta y by delta x will tend to instantaneous value at A if B approaches point A or delta x tends to 0. Delta x tends to 0, that means A and B points are much closer. Now, the idea here is we'll get instantaneous value of rate of change of y with respect to x at A if B approaches point A. If B approaches point A, then the average value will be as good as the instantaneous value. Let's try to understand what happens if B point moves on the curve, what happens to the slope of this line, because slope of this line is the measurement of average rate of change. Whatever will happen to this average rate of change or slope of this line as B approaches to point A, in the end, that will become the instantaneous rate of change of y with respect to x at A. So what we are going to do is move our point B to B1, then B2, and then B3, and finally very close to point A. And we'll see what happens to the slope of this line, which is the average rate of change. You can quite clearly see the slope of this line changes, but it still cuts the curve at 2 points, at A and B1. Then the slope has changed and it cuts the curve at 2 points A and B2. When you move to B3, the slope has changed and it cuts the curve again at 2 points A and B3. When it comes very close to point A, you can see there is no measurable difference between A and B such that graphically it would mean that B coincides with A, and earlier it used to cut the curve at 2 points. Now it will cut the curve at only 1 point because A and B will coincide, and then you can see it will become the slope of this line is same as the slope of tangent at A. So let's record this observation. The instantaneous rate of change of y with respect to x at A is simply slope of tangent at A. What does that mean graphically is under the condition that delta x goes very small, that means point B comes very close to point A, this average rate of change is equal to instantaneous rate of change at A. So it would mean there is some mathematical condition that delta x tends to 0 under the limit that delta y by delta x under the limit that delta x tends to 0 is equal to instantaneous rate at A. Now we can define instantaneous rate of change of y with respect to x at any point. And from the graph you can see it is also slope of tangent at A.